Okay, in this recording, we will be talking about adjustments and transformations of the time series. So, these are types of pre-processing of the time series, and maybe we have done some of them, and we have still have some left, some steps. And we talked about the pre-processing. It's that everything we apply to the raw data to make it just simple, more stable, and more suitable probably for modeling or forecasting. It's just similar to the data cleaning in when we do data analytics. Here we call it just a pre-processing. So why, the question is, why do we adjust and transform the data? Because as we said, we want to forecast or analyze the patterns in the time series. And we would like to have a simple and consistent data as much as we can. So we have adjustments, we have transformations, we have smoothing, we have differencing and decomposition. And for the adjustments, the one that we're going to do today is we are going to, the goal of this is removing the external effects. And we'll be covering some examples like adjustments or the calendar adjustments and inflation adjustment and population adjustments. After that, we'll be discussing quickly the mathematical transformations. And the goal of this is to stabilize the variances. And the techniques that we use using logarithmic power, square root, or more generally is the Cox method. Smoothing, we talked about smoothing. The goal is to reveal the trend. Examples about that is the moving averages, and we did differencing, which is when we removed trend and seasonality. Finally, we will be doing as well the decomposition in the next recording. The decomposition is how to separate the components, and we will be discussing two types, which is the classical decomposition and STL. Okay. So the first one is the calendar adjustments. And when we use the calendar adjustment, we use the calendar adjustment when the time series relies on the number of days in a period. For example, monthly sales, production, or electricity demands. As we know that some months they have 28 days, 29 days, and 30 days, and maybe 31 days, right? So if you record, for example, the total sales, the month with more days, more trading days, is going to be automatically higher than the one that have less number of days, right? So the variation, the actual variation here is not real change in the behavior. It's a calendar artifact, right? So the question is how to fix this. We just compute per day averages. We just divide the total monthly sales by the number of trading days, and this will remove that artificial variation. We can see from this example that, like this month, we have 31 trading days. This month, we have 28 trading days. So the total sales here is logically going to be higher than this sale, sorry. So what to do, we just divide them, we get 10,000 sales per day, and look at them, they're ISM, right? So we would like to get a series that reflects what's happening, the true economic or business behavior. We don't want something to give you false information. So that's why we do the calendar adjustments if needed. The second type of adjustments we normally do, which is the population adjustments. And this happens when the variability grows or shrink with the population size, like the GDP, number of hospitals, beds, number of crimes, number of cars. So we want to know if the growth is real. If the growth is real or just because there is more people. So for example, if the population doubles, total GDP should double because anyone being richer. But GDP per person reveals that whether living standards are improved. So to fix that, we just divide the total measure in this case by the population. And we can see in this example that in 2000, we have the population were 20 millions. So the GDP was 400 billion. In 2020, the population rose and became 25 million, and the GDP is 500 billion. So this is normal increase in the GDP. However, to measure the wealth of individuals, you have to divide by the population. So to get GDP per capita, we get $20,000, 20,000 in both days. So now we removed what we call the population effect. So that give you clearer view of the true productivity or efficiency, right? Because this growth is not real. It's not really growth per person. We are speaking about, it's not 25% as it shows here. So that's why we use the population adjustments, just to take off the effect of the population. The third one, which is a very famous one, it's the inflation adjustments. And when working with money data over the time, like prices, wages, GDP, houses, prices, then we have to think about the inflation adjustment. Because why is that? Because the purchasing power changes because of the inflation. Like if you buy a house in 2000 or in 1990, as you see, suppose that it's $100,000. This is not equal to the $100,000 house in 2025. So without this adjustment, it seems like everything always increases. So how to fix that? We convert all of the dollar values into constant dollars relative to a specific year. So we have a specific year, which is we are going to call it base year, and we use a price index indicator. So the price index, one of the indices, we call it CPI, which is the consumer price index, or the producer price index. It depends on what kind of data you're working with. But we just divide the original data by the price index at time t, and we multiply this by the price index of the base year. You choose the base year. For example, in this table, we chose the base year to be the 2010. The house price, for because it's the base year, the CPI is 100, just 100% or just 100. That's why when you do the math here, when you use the math, this equation, you get 400,000, the same number, because this is my base year. And what does it mean, my base year? It's the one that I'm calculating this is the one that I'm relying on. This is the one that the dollar, or I compare the dollars based on this year. So in 2000, the house price was 200,000. The CPI is 70. So when you do the math, when you divide 200,000 divide by 70 times 100, what do you get? You get $285,000 approximately, 286,000. So when I do the comparison now, I can compare both numbers, both numbers, not the 200 with the 400. So you have to adjust every year based on their the base year. So now these have equal value in terms of dollars. These two do not have equal values. It's kind of, we are adjusting for the inflation, because here the prices looks doubled. In fact, they are not doubled. They're less than, only 40% more. So in this case, we have more accurate data, so we can build our models based on this. The final thing that we do is kind of a transformations, and